Okay, Bismillah, Alhamdulillah, salatu wassalamu ala Rasulillah wa wala. Assalamualaikum and good evening, everyone.
Good evening.
I'm really sorry for the last week because unfortunately the place that I went it doesn't have a really stable internet, so I have to cancel the class. But we will have to do some makeup class for that, 3 hours. Maybe I will tell you about. I will tell about that later after maybe after week 7. Okay. So my question is there anybody who still does not have their matrix number? Anyone here who did not have matrix number? All of you has your matrix number? Because last time there's one or two person. Okay, so since no one is replying, so I assume that all of you has your own email address from UPM, right?
Yes, doctor.
Okay, because I want to make sure that all right. Because last time during the quiz, I just put anybody who with the link can open it, but now I think it's more secure if I put people that have university email to answer that quiz and also assignment and so on. Okay, now let's move on to our topic, modeling method. Okay, so if you remember last time, we tried to model using change, and from the change, we are trying to find the changes. And from that change, let's say delta A, this is equals to next time step minus the previous time step. So this is, we want to find the changes. And then we say the changes is proportional to some, to its, let's say this A n, something like that. So, and it depends on your, it can be something like that. And then you say that we have some constant times a n. Okay, so we want to find the changes. Is it going when the change is increasing? Is it when not the other way? When something increasing, does the change increasing or decreasing? So we talk about proportionality. The proportionality of that, let's say from y to x, a simple one. And then we also talk about things that to neglect, why, to make our model simple. So we neglect some things. So that is our assumption. And the things that we neglect must be make sense. It's not just you neglect everything. It's something that is makes sense to neglect. Maybe too small, for example, gravitational force, or maybe friction or something like that. And variation of temperature within a body. So something that things to neglect. And then we also talk about dynamical system, which we trace the points. And then let's say last time we talked about the point data in points, and then we trace the plot and so on. All right. And then we also talk about discrete and continuous, the difference between discrete and continuous model. And this comes to our another one, which is the difference between difference equation versus differential equation. So bear in mind that discrete refers to difference equation and continuous is from differential equation. And then after that, we did about numerical solution. So numerical solution is when we put our during iteration and to get all, let's say all n's, all value for n's, all value at n times. You cannot submit your attendance. You need to, if you want to submit your attendance, is it a Google Drive, right? A Google Drive, Google Form, right?
Yes, doctor, but from my side, it says you've already responded and you can fill out this form only once.
Yes, you can only do it once. Okay.
But I haven't filled in for today.
All right, right. I will change the setting. It should be 14. You need to be able to do it for 14 times. Okay, so I will change the setting during the break, all right?
Thank you, doctor.
Welcome. Okay, so we talk about this numerical solution is the data that we get from iteration from difference equations. Okay, that's just a review. Now when we go to the next one, this is also related to proportionality. Proportion. For example, if I take a model of scale 1 and L, 1 ratio L, for example, this is the length. This is the length. And then the surface area is the ratio will be 1 ratio L squared. So this is L, and then this is the L squared. And then if you consider the volume, it will be L cubed. So it depends on your problem, and you need to be careful with this ratio. Okay. For example, in this case, take an example of packaging costs. So the cost to package some product. Why is it that larger packages cost less per gram compared to small packages, smaller one? Okay, why is it? You can, this is question mark. And then what are the factors that contributing to such differences? You need to identify what are the dependent variables and the independent variables. And then is there any other variables contribution to the cost? So you need to understand this. This is maybe four questions for you to answer in order to model your packaging, the cost for packaging. So that's just, you can have more than 4 and so on. Okay, so we need to find out what makes the difference between the size due to the weight or maybe due to the volume. Okay, because sometimes, for example, a big one, let's say this one, let's say box number 8, this is A, and then box B. Okay. Let's say A and B has the same weight. Weight of A is equals to weight of B. But why is it that this one, B is bigger, the volume of B is bigger than volume of A? So does it mean that cost of B is bigger than cost of A? Is it like that? Or maybe we can also reverse this. We can say that, for example, volume of B, even though volume of B is bigger than the volume of A, but the weight of A is bigger than the weight of B. For example, you can have a box of, this is like a box of, let's say this is some, let's say this is some iron in this case, iron oxide maybe. I don't know, just an example. And this one contain cotton. So obviously this one is it going to be, what happened to the cost of packaging, something like that. So it depends on, so the cost of packaging in this case, we consider weight and also volume, right? So let's try to figure out. Let's take an example from wholesale cost. So this, the packaging for wholesale price. Okay, so one example in this case is, let's say A is the cost to produce the product, cost of production. And then B is cost to handle the package. And C is the cost for shipping. And then D is the cost for material. So these are, all these four factors are the related to the cost. Okay, for example, production, cost of production. So an example maybe a durian. Say durian maybe versus, let's say cotton. So it depends. You don't produce durian. Oh, okay, maybe this is one. It wasn't a good example. Let's say water bottle, mineral water. Versus can soda. Something like that. Okay, so the product for the same volume of water, it will be a different weight, something like that. And then the cost of packaging, let's say how many people are going to have it, and so on. Shipping, of course, transportation and packaging material. For example, you want to have a really good box compared to a really bad one. Okay, so that one is also contribute to the cost. Okay, any questions so far? Are you guys okay? Any question?
Not yet, doctor.
Not yet. All right. So, what's the relationship of these variables? Okay, which are independent variables, and which are the dependent variables? Okay, what do you think? Which are the independent variables? Which are the independent? From, let's say, this one. Any ideas?
Maybe cost of production, doctor.
Okay.
Or
Any other answer? Ada jawapan lain?
Cost of shipping, doctor.
Yes.
Independent.
Independent? Which one?
Yeah. Cost of shipping.
Cost of shipping.
Yeah.
Okay, so one of you say this one, let's say this one, and one of you say this one. Okay, now let's try to understand this problem. Okay, the wholesale cost. Okay, I'm asking about independent variables. Okay, so what does it what is it depend no, it's not depend, it stand by itself, so it doesn't depend on any other things in this case, which means that other variables doesn't affect this one. For example, so if you want to understand this, actually the answer will be the independent variable is all this form production. One is production, and then this shipping, because production and shipping does not relate to each other. There's no way that production and shipping is related to each other. So this is independent with each other. Shipping, and then what else? The other two is material and packaging. So these are independent. It doesn't however, the dependent variables are the cost. So the cost depend on production, depend on shipping, depend on materials, and also depend on packaging. Does it make sense? Does it make
Yes,
sense?
Yes,
doctor.
doctor.
All right.
Yeah.
Yes, doctor.
Okay. Now, that one is just, I want to give you an example. I'm not going to like create a problem or something like that. So sometimes you have too many things and it's hard to decide which one is dependent on each other. So let's say maybe we can say something like this. We can say, let's investigate how they are related. We can say cost, just give you an overview. The cost of, what does it, the cost of price, the price depend on the cost of packaging. Okay, the cost might be, you can say, is proportional to A, let's say K1, maybe K1 factor 1 plus, no, we don't have a K1 yet because this one is still, we are using the proportion. There's no constant if you are using something like this. Okay, so the cost is proportion to A plus B plus C plus D. So this is the cost of production. Let's say I'm talking about, this is 1, 2, 3, and 4. I think it's the other way around. This is 3 and 4. So this is related to number 1, production, and then related to shipping. Then this is C, the packaging, number 3 and number 4. So the cost is proportion to these things. And then since you are talking about weight, you can assume, this is your assumption, assume that volume is proportion to weight. The other way around, weight is proportion to volume. Okay, just assume like that, because for example, if you have a bigger volume, it means the weight is bigger. If you have a small volume, then the weight is small. So that's my assumption. So we're still talking about the proportionality. Okay, so for example, if I want to talk about the material, maybe the material is depend on the surface area. Because why surface area? It's not the volume. Because, for example, if I have a box, this is, let's talk about material. Material using surface area, because let's say how many ringgit per area. Let's say you have a box like this. Okay. So the material that you are using is just this one, not the anything inside. So if you open it, it just looks like this. Just a simple one, for example. So this is your surface area. And then shipping. Shipping, it depends on what? Maybe it depends on the type of postage that you are using. For example, maybe you have several options. You have Lalamove, or maybe what's JNT, or Post Laju, or maybe some other else, Grab, and so on. Grab Express. So it depends on that, and production and so on. All right. So, however, in this case, we are not talking about the detail, but we just talk about what's the main important variables that we want to consider. Okay, so you can see that in some cases, if you think that this is too much, then I can eliminate some of my variables. For example, maybe the shipping cost, the cost for shipping. Let's say if it doesn't matter if I use a different shipping company, they charge in the same thing, except that the difference is just the time that it will take to arrive. So maybe you don't. That's not an issue, because the cost will be the same. So you not consider about that. It's something like that. Okay, now, so these are the things that you need to consider: the scale and sizing when you make your modeling something. Okay, so when you model a problem, you need to consider about scale and the sizing, the ratio of things. For example, if you are interested in biology, maybe some kind of about animals and so on, you can try to ask yourself, for example, in this example, is it true that smaller animals has higher heart rate than bigger animals? So you are talking about the sizing right here. Is it true? Because I think in most cases you can see that birds they has higher heart rate compared to elephants. That's just two species, but how about in general? Okay, and then how to verify this claim? How to verify this claim? Why is it important about this scale and sizing? So maybe it's related to cost of using modeling and so on. Maybe you want to take some experimental data. So it depends on your purpose of modeling a problem. Okay, free fall. Do you know what free fall is? You know what free fall is?
Is it like jumping down or falling from it?
Yeah, falling from the top and go down. All right. So let's say, for example, free fall. It's not you, but maybe you drop something and from above or something else. If you notice that, for example, if you have a paraglider, some paraglider use something like this. Not paraglider, parachute. Some parachute looks like this, I think. Yeah. Okay. And sometimes it looks something like this. Just a simple one. Okay, why is it what's the difference between this and this? So how, because we know that this two is to slow down the falling speed, but why is it, which one is better? Is it this one or is it this one? Okay, and then if you have another question, does weight play a crucial role in its speed? For example, if you have a lemon right here, this is a lemon falling versus, let's say, a TV. This is a TV falling. Okay, is it going to be, the speed, is it going to be the same? Something like that. Or does it depend, why is it that if you have a sphere item versus like, for example, a flat plate, something like that. So does it matter if this one has the same amount of weight compared to this one, but this one is you have larger areas. And so on. So this is important. For example, you can apply this. You can apply this to. You can apply this to, for example, if you fly an airplane. Let's say you have an airplane, a simple airplane. Okay, so let's say the engine is burned, maybe it's burned down, for example. So how does engineer design this so that it will be able to land safely? This is the same thing, but in different in more detailed version. Okay, so more detailed. Okay, but a simple thing is that actually weight play a crucial role too, but not crucial, just a simple rule. But the only thing that is important is surface area. So the first surface area is crucial in free fall. All right, and another thing that you can ask yourself, or maybe if you have any interest, why is it that some countries have different sizes of banknotes and some don't? For example, if you go to the United States, let's say US, all money, no, the paper money has the same size. Malaysia is different. Why is it? And Malaysia also has different color of banknotes, but United States, the color is the same. So sometimes $10 you can confuse with $1 and so on. The only difference is just the face on the notes. So you have to be careful in that. So why is it that they make it that way, and why is it Malaysia is different than other country, and so on? Is it because they want to save some cost? Is it because something else? Security and so on. And this is also a good example of sizing and scaling. Do you really save on gas if driving with closed windows? Okay, because have you heard about when you close your window, you are going to get faster, and when you open your window, you are going to get slower, and then you are not going to be able to save
Hello.
on the gas. Yes.
You hear me?
Yes. Any question?
No, but my mic is not working.
Okay.
I test it now. I'm sorry.
It's okay. So this is an example. Or maybe you can say, do you really save on gas if driving with closed window, without AC, without aircon, or with aircon? By the way, before that, I want to ask you something. Are you guys doing master by research or by coursework?
For me, by research.
By research. And other people?
By coursework.
Coursework. Okay.
By
So for the
coursework.
coursework, so you don't have your proposal yet, right?
No, doctor.
For some of us is already on the final sem. So
Okay.
okay.
So you already have your final sem coursework.
Yes.
Okay.
Yes, doctor.
So is it like but you have to have a dissertation, right? You need to write something, right?
Yes, so we have dissertation part B for this semester. So proposal is last semester.
Okay, so you already have your own modeling problem, or maybe your own problem to solve.
Yes.
Yes, doctor.
Okay, so and all of you has different kind of problems, right? One is statistic. Is there any statistician here? No, right?
Yes.
Are you statistician? So one person is statistics, from statistics. Okay, that's okay. And the other one is
Doctor, some of us don't have a problem yet because we are from the first semester.
so yeah, okay. Because I'm doing this because the examples that I'm going to show maybe today or maybe next week, it consists of a variety of topics. So because you don't have any for those who are newly in this master program, maybe you can just learn a lot of things, and for those who are already have their own problems to solve, you can also learn about other problems as well. Okay, so now I'm going to talk about the types of behavior. For example, the behavior of solutions from the data, from the theories, and so on. And then from this behavior, we want to find the mathematical formulation of it based on that behavior, and then we form an equation. All right. Now, if you want to build a model, first thing, you need to formulate the problem, not formulate the equation, but you need to formulate the problems. What is it that you want to know? For example, somebody wants to find out, to predict, let's say, voting numbers, maybe from a government and then from your opposition, and also maybe from, that's two competing variables, and maybe you can have another one, independent parties, and so on. So that's three competing problem. So first thing is you need to formulate the problem. For example, in my case, I'm using differential equation, partial differential equation, and the problem is about high-speed jet flow. So if I talk about high-speed jet flow, meaning that I need to consider compressibility in fluid motion. So when I consider compressibility, meaning that I cannot use hydrodynamic model, so I need to use gas model. Okay, and that problem, that equation has already been studied for centuries, and that one of the famous is called Navier-Stokes, and maybe a simple version of that is called Euler equations. So we have the theories, but it's still in many of the solution is still in progress. All right, so you need to understand you need to know what you want to know. Okay, that's just a simple word for that. Okay, and then number two, you need to outline the model. By outlining the model, you need to notify the important and the unimportant relations between variables. Is it useful? Is it useful? When you say that it is important, is it useful? And can you obtain data and use it for prediction? For example, maybe this is just a rough estimation. It's not necessarily accurate. Okay, the first thing is do not seek for perfection yet. So it's not necessarily accurate. This is just to test your understanding of the problem. Okay, and then after you have built your own model and then formulate the problem, now you need to test your model. So can it make prediction based on that data, or maybe common sense? However, you need to also consider ethics. This part number four. Sometimes you can't do it. Why? Why do you think sometimes you won't be able to test your model? Why? What do you think? Why? I put it here. But from your opinion, why you cannot do it? Why you cannot test your model in some cases?
I think because sometimes it's ethically wrong. For example, in biological invention, when they do cloning, sometimes it's ethically wrong to like clone human. So it's wrong to test the model. Is it like that?
Yeah.
Or makeup testing, yeah. Makeup testing on animals.
Yeah. So you need to consider that. So sometimes
Yeah.
you need to consider ethics, and also you need to also think about dangerous situation. Dangerous situation. For example, you can let's say you want to model example, let's say above example right here. I want to model,
Yeah.
yes, a blast or maybe a nuclear reaction, something like that. So this are a very dangerous situation, and it will cause a global panic. So you can, in this case, you cannot test your model, but the only thing that you can rely on is your simulation. Okay, and another one, this is ethics, and then number 2, dangerous, and number 3, maybe because too expensive.
Yes.
Too expensive. For example, um, what if you want to test a cell in maybe in vacuum atmosphere, or maybe in outer space. So that is too expensive unless you have some sponsor or something like that. But if it's too expensive, then you can just leave it as it is. So just or maybe you can ask help from some other country and so on. So, but sometimes if it's too expensive, you just say, okay, that's just my prediction. And if someone can continue my work, then please do so. Okay. He said that is just some of the reason that you cannot test your model.
Yeah.
Yes. Okay, now how to formulate your problem. In this case, how to formulate my solution or maybe equation. So one of the method is method of conjecture. So you have, this is like your, in simple word, this is your gut. So you say that, okay, my gut saying like this. You try to hypothesize the form of the solution. Okay, now you say, this is my solution. And then you can reject or accept that hypothesis based on observation or exploration. And then you can discern the pattern and then solution. For example, if I have my data, let's say this is my x-axis and y-axis. So let's say if my data looks something like this, okay. So I can say that, okay, that looks like a linear line. Okay, so this is your observation. I know this is not really a good approximation. It should be this one, but just understand that this is, you can see that this looks like a linear line. Okay, you can discern the pattern and then solution. You can say, okay, maybe because this is start from 0, I can say y equals to mx, something like that. Okay, now let's see some other pattern. Okay, let's see this one. Let's say I only have 3 points. 3 points, x and y, and I have 3 points. Like that. Okay. Now you can see that you maybe because of time constraint, you don't have enough time to take more data, for example, and then maybe I can say, okay, this roughly looks like a straight line, roughly. Or maybe, maybe your friends say, no, I don't think that is a straight line. It can be a quadratic, something like this. This is case number 2. Or maybe another person, this is case number 1. Okay, maybe another person say, okay, I don't think that looks like a quadratic. It may be a cubic function. Because why? Those are, you remember about scaling that I told you? So let's say, let's try to make it as cubic, maybe something like this. I don't know, something like this. Okay. It's not a good approximation, but remember about scaling just now? So this formulation of your equation, formula of your solutions, will affect your future prediction. Okay, so for something like this, in cases of like this, it is better if you don't think that you have enough data, then of course you need to make one is number one, take more data. So usually this one in case of empirical problem. Okay, number 2, you don't have to take data, so you can just refer to existed solution. Okay, so this is your, let's say, deterministic problem model. Okay, so you can either you can have either two of these method, extra method to discern the pattern and then the solution. All right. Now, before we can okay. I'm going to have until 8:40, then we can have a break or 5 more minutes. All right. Method of conjecture. Okay, example. If you remember from our previous example, saving account, we have, this is your difference equation. Okay, and using C++ or maybe C or MATLAB or etc, you can plot the data. Okay, so if you plot the data for 12 months, this is your output. But if I plot until 500 months, okay, you can see the difference. So initially you say, okay, this is straight line now. No, this is no longer a straight line. This is looks like an exponential. So what we are talking about is only at this point that looks like a straight line. So you can see the difference. All right, now let me see. Okay, 10:35. Okay, maybe we can take a 5, maybe 10-minute breaks. Maybe you want to pray or something. Okay, take 10. All right, we'll continue. Okay. 8:45, all right?
35?
8:45.
8:45. Okay, thank you.
Yeah. This is my initial condition. You can say A naught, or maybe you can say not necessarily A naught. Maybe you can say C or anything else. So this is your rate. Okay. So the good thing about this is that this formula allows to calculate specific balance at certain time. Okay. Unlike before, if you want, let's say before you have this formula, you want to find like A45, the 45th month. So you need to calculate one by one. You need to know the previous values. Okay, if you are using the discrete formula. But when you have your problem and when you have your solutions that you can find at any specific time step that you want to know. Okay, now this calls to long-term behavior. So when you see something like this, you are talking about what happened as times goes to infinity, or maybe what happened in a long time, not necessarily in infinity. Maybe at the end of your term, what is going to happen. So we need to find the long-term behavior. Okay, in this case, before we go to that, the summary of our method of conjecture is that, first of all, you need to observe a pattern. One is you can observe by graph, or maybe you can also by algebra manipulation. Okay, and then you conjecture the form of that solution from this pattern, and then test the conjecture by substituting your solution, and then you accept or reject based on that substitution. And this is substation. This is not subway, substitution. And then for substitution, you need to make sure that the result must be identity, meaning that the result must be identical in order to accept it. Yes. Yeah. Are you trying to ask question?
No.
Okay. Now, we are. What happened? Let's say what happened if R, this rate R can be negative and positive. Okay, so this is what we did just now. What happened if the R is negative or positive? This is the solution. This is your theory. If you have something like this, okay, I'm going to go fast. For example, we are going to talk about this after this, negative and positive. This is about long-term behavior. Okay, now before we go to the is it negative or positive, I want you to look at this example. This is sewage treatment plant process. So this is like to remove the contaminant, and I want to see whether how many percentage of contaminant will be removed from the sewage. Okay, the process is that at each hour, 12% of remaining contaminants will be removed. So 12% each hour will be removed, meaning that you are going to remove 0.12 of the original contaminants. Okay, and then the question is asking what percentage of the sewage will remain after 1 day, meaning that what percentage of the removed contaminant will remain. And then how long, this is question number 1, Question number 1. And then question number 2, how long it will take to lower the amount by half. So meaning that by half, meaning that half of that concentration, initial concentration. And the same thing, how long until the level of sewage is down to 10%. So 10% meaning of the original level, so 0.1 of the initial condition. Now, first of all, is how to formulate my problem. Okay, I think I have one space right here, but that's okay. Let's see. Let's try to write it right here. Okay, now if I say something like this, this is let's say let C is the C naught is the amount of contaminant at 0 hour. So this is our initial condition. And then I say Cn is the amount of contaminant at nth hour. So it refers to Cn. Okay, so meaning that if I want to have n plus 1 at n, and then n plus 1, the next n plus 1. So I can say n plus 1 in the next, after 1 hour. Okay, after 1 hour, I need to remember that each hour, so each increasing hour, 12% will be removed. So meaning that I need to have C of n minus 12%, which is 1/2 of Cn. So this means that I have only 0.88, only 88% of my original concentration. So this is from this statement right here. Okay, now I have my formula. I have my formula, which is Cn plus 1 equals to 0.88 of Cn. So this looks like what we have before, which is An plus 1 equals to R times An. Okay, now we have this formula. What percentage of the sewage will remain after 1 day? 1 day, how many hours? 1 day is 24 hours. Okay, so meaning that I need to check after 24 hours. So do I have to do this 24 times? No, you don't have to, because we already know the solution to this dynamical system is that to this problem is C of k equals to R of k times C of 0. Okay, so this is equals to 0.88 k times C naught. So you can see that what is k? K is the number of hours. So k equals to 24, and then solve it. Solve for C. Okay. So I don't want to solve it, but if you want to check your answer, you should be, the remaining time is just, what percentage? This is just 4.65% of original concentration. So 4.65. You see that it is not given. The original concentration is not given, but the thing that is important right here is the percentage, because the initial condition is not given. It's not a problem. All right. Any questions so far? Any questions so far? No.
Doctor, I have a question.
Yeah.
So, for example, for this problem, right?
Yeah.
The initial amount of contaminant will definitely be 100% in the
Yes.
beginning because we
Yes.
haven't reduced it. So, does it make sense if the formula we just remove the C naught because it won't change and it's gonna just be 1, or so it's just gonna be RK, or do we still need to include C naught?
No, it will be removed because I told you just now, actually, if you solve this, you can cancel out the C naught. So that's why I said the C naught is not an important factor in this case. Maybe I can show you. Let me show you the.
Okay.
Let's see.
Okay, thank you, doctor.
No problem. Okay, so for example, what was the question? Okay, so we are looking at C24 after 24 hours. Okay, so C24 is just 0.88 times times 20, not times, it's to the power of 24 of C naught. Okay, so this is equals to what? Equals to 0.0.0465, I think. C naught. Okay, so you can see that if you solve this, C24 is just 0.0465 of C naught. So this is your percentage remaining of original concentration. So it doesn't matter what the value of C naught is, but at C24, the only amount that is remaining is just about 5%, less than 5%. So you can say there are two ways to say about this. One way is you can say less than 5% remaining, or another one I can say more than 95% is removed. So those two are similar connotation. Okay, is it clear?
Yes, doctor. Thank you
Right.
so much.
You're welcome. Okay, now do you want to know about this one by half? So if you, I'm going to show you how to do it. For example, to lower the amount by half, meaning that 0.5. So 50% is just 0.5. So meaning I'm looking for C of K 0.88 of K when this is let me rewrite this again. Okay, I'm looking for something like this, 0.5 of my original concentration. Okay, I'm looking at this original concentration. So this is C of K. And this one is equals to 0.88 of K times C naught. So you can see that you can cancel out C and then solve for K. I think you know how to solve it. This is a basic logarithm. Okay, the same thing for this one, 10%. 10%. So this is just you can see that you can say 0.1 of concentration and so on. You can solve and then solve. Okay, so this is easy. So but if you want to know the answer, this one is, I think, by half. I think this is about 5 hours. I think about 5 hours. And this one is about 18 hours. All right. Now, this is the plot if you're using using C++, solution using C++. Okay, you can see that this is my solution using difference equation. So it's easy compared to that one. Okay, let's see. Remember, I start from concentration of 10. I don't know just give a value. So for example, just now I'm looking for time is 10 hours, so I cannot go to 24 hours. Let's try to look at this one. Lower the amount of sewage by half. So let's say 10 half is 5 is located about this. No, somewhere here. I'm sorry, my hand is shaky. Okay, so this is about 5 something, close to 6 hours, but less than 6. Okay, this is amount half of the C naught. All right, and then look at this one, down to 10%, down to 10%. I don't have 10% is just 1. I didn't have that on my graph, but you can see that this is almost the same. If you just calculate using this or you using graphical interpretation, it will be the same, but you need to find out the exact coordinate in order to have exact number. Okay, now let's talk about just now that's easy because we have a positive before positive rate. And let's talk about this one when we have a different number of rate. So case number 1, when we have rate is just 1. Okay, now if I take this rate equals to 1, an plus 1 equals to 1 times an, so that is just an. So meaning that this is a constant. Nothing changes. So if I start from any number, it will end at that number also. So if I have this one, let's say this is my x-axis. If I start at positive, let's say a naught, and then it will be the same at any times. And if I start from negative a naught, it will be the same for any time. So this is time, excuse me. This is time and time. Okay, now if we are looking at r bigger than 1, we already saw this. We already saw this in our previous example of saving account. So you have what? You have an plus 1 equals to 1.01 of an. And if you remember that our graph looks like this. So this is increasing without boundaries. What happens if you have r is less than 1? And what happened, for example, if I have, this is a positive, let's say between 0 and 1, no, maybe I can include in this part because this is also included. Okay, let's talk about this one, case number 4. You can see this is an example of, I think just now we have a concentration, let's say positive. Example just now is that an plus 1 equals to 0.88 of en. So you can see that already from this graph that the long-term behavior, when t goes to infinity, it will die out and to any value, or maybe to negative values and so on. All right. So now let's try to look at the behavior when you have a negative values. Okay, if I put my r, let's say between -1 and 0, this is r between, meaning negative. Okay, why is it like going up and down and increasing? What do you think? I think this is just less than 0. Okay, why do you think it's going up and down?
I think because it could be to the power of odd or even number. So it could be positive, it could be negative. The r could be positive or negative depending on the power.
Yes, it is exactly. It is exactly because if you look at this one, say an plus 1 equals to minus r of n. Let's look at this one. Just hold on. Not c, a of k equals to minus r of k an. So this is alternating between negative and positive. If k is odd, then it will be negative. If k is even, it will be a positive. So that's why this is alternating between positive and negative values. And this is growing. All right, now, for this is, I told you just now. Okay, now, yes, so this is right. So this is less than 0 and big. Okay, what happened? This is a fraction. This is a negative fraction. So we can say that the behavior, this is long time behavior. This is a big one. This is, we can say this is oscillation, oscillatory. And this is also oscillation, oscillate. But for some reason, because this is a fraction, and it will goes to 0. Because why? Because when you have, let's say, a of k equals to minus r of k a of n, a of n is 0. So for a very small value, as r goes to small value, then the fraction of this will be goes to 0. So that's why we have this one 0, because this one is really small as power is goes to infinity. Okay, so this talk about the sequence. Remember that before in week number 1 we talk about sequence. So this is similar to the sequence. Okay, now this is just summary of our interpretation. For example, we did just now r bigger than 1, and initial condition is positive. So we can say that grow large without boundary. And if we have a negative initial condition, it will grow negative without bound. So you need to understand this one. Just understand this one, then you'll be fine. R of k times E naught. If you understand this, no matter what, you can see that you can understand the behavior for the long term behavior for the long term. All right. Okay. So which one do you want? Which one you don't want? It depends on your problem. Maybe this is okay, and maybe this is not okay. Examples. One of examples, perhaps for oscillation and decays, you can look at spring and spring damping. Okay, sometimes you can have something like this, and sometimes you have just a single dip, something like that. Okay, so it depends on your actually this one also depends on your physical behavior. Okay, now when we talk about long-term behavior, this is actually what we really interested in, which is equilibrium. So equilibrium is what? This is in physical. When we talk about physical, these are opposing forces or action are balanced so that one is not stronger or greater than the other. For example, supply and demand were in equilibrium, so supply and demand is the same thing. Chemical equilibrium meaning is talk about reaction, chemical reaction process, and maybe this is just balance or calmness, or maybe we can, in our case, when we talk about equilibrium, we talk about the long-term behavior, the value that we approach. So we talk about long-term. In our case is this. Okay, now, so in our interpretation, when you have, let's say you are using A, A is an equilibrium for this system, dynamical system, if and only if A is equals to FA when you start initially at A not equals to A. So for example, maybe you don't understand this, maybe it's quite confusing. Let's talk about this one. Drug prescription. This is not actually not real drug. Consider the decay of this one in a bloodstream to prescribe a dosage that keeps concentration between acceptable level. Okay, in this case, acceptable meaning safe and effective. It's not too much such that it will be dangerous, detrimental to your health, or maybe it's not too low such that it will not be effective. So it's between safe and effective. Both should be fulfilled to be at acceptable levels. And the daily dosage is 0.1 milligram. And then half of the apotoxin remains in the system at each dosage period. And from this information, we can formulate our discrete dynamical system. So this is your dosage you put every day. And this is your rate. It remains in the system. So this is just a crude assumption. Why? Because you're not talking about what happened if you went to the bathroom and so on. Or maybe you do some exercise and so on. It's not taken into account. So this is just simple model. Okay, now consider 3 different initial dosages. So we consider 0.1, 0.2, and 0.3. And we want to plot the numerical solution. Why we do this? Because we need to observe long-term behavior. Okay, so we need to observe so that the drug remains in your bloodstream is safe and also effective. For example, if you take vitamin, are you going to take vitamin every day, or maybe you want to take vitamin every other day? Okay, maybe twice a week, or maybe one every 2 days, and so on. So you can also apply that into your own problem. Okay, the thing that important right here is we need to observe long-term behavior based on initial condition. Okay, now let's see. Okay, I did not write. Okay, so this one is d naught equals to 0.3, and the red one is d naught equals to 0.2, and this one is d naught equal to 0.1. Okay, as you can see that no matter what value, what initial value you put in, the solution will end up at 0.2. So if you just let's say make it into 0.4, it will also end up at this value. So you can say that this is my equilibrium value. And this one is a stable. How do I spell that? Stable stable equilibrium value. Because why? Because no matter what point you start, you will end up at the same place in the end. Okay, so that is stable equilibrium value. Now let's look at another examples. Okay, any questions so far before we begin? Before we go now to the next example, no question, I presume. Okay, no question. Okay, can I go on or am I going too fast?
So far, okay, doctor.
Okay, okay, thank you. Thank you for responding. Let's see example number 5, annuity. Do you know what annuity is? Anybody? Do you know what annuity is? An example is that you owe some money. You owe the bank some money, and then you pay that money to the banks monthly or maybe yearly and so on. And then it will be at the end of the time, the value will be 0. Or sometimes you can also have something like this. You invest initially a really huge amount of money, and then you can take you can take some part of that money each month. Okay, so this is the difference. You can see that this the difference between saving, and between saving and this annuity is this value. Okay, that is negative. Yes. All right. Okay, so what do you expect the numerical solution to behave? Based on our previous example like this one, okay, based on this graph, okay, what do you expect the numerical solution to behave? Meaning that is it going to grow, or is it going to decay, or is it going to be a constant? Constant, of course, it's impossible for constant, because now you have r equals to 1.01, which is bigger than 1. So maybe you can expect the solution, is it either growing or decay? And let's try to investigate this. So you start initial investment at 90K, 100K, and then 110K. So we want to find the equilibrium value. Okay. If you plot using C++, let's say, so this blue line is the 100K. This is exactly 100K, and this is 90K. So this is different. You can say that different initial condition give different long-term behavior. Okay, and actually there's no, for this one, there's no equilibrium value. for this one and this one. No equilibrium value because it does not goes to a specific value as t goes to infinity. Okay, but as you can see that when you put 100k right here, it will be a constant value. So meaning that you can apply a equals to f of a. So you can say that in this case, 100k is the equilibrium value. But an unstable equilibrium. This is not stable. So you can understand, for example, in terms of, let's say, if you are going running on a hill, something like that. This is your equilibrium. You can go this way or that way. Okay, so it's not stable. Now, example number 4 and number 6. All right, I think we can take maybe we can take 10-minute break. Take 10, or maybe no. I will just finish this one and then we can take 10-minute breaks. Okay, now let's check checking account. What does it mean by checking account? Anybody knows about business or banking? Checking account. I'm not sure if Malaysia have one, but overseas this is really checking account is usually used by students. You don't know what's checking account?
No, doctor.
Okay, so checking account, if you say something like this, I have a checking account, meaning that no interest. For example, if I put 300 this month, the next month is just 300. If I didn't put anything else. Okay, so it will remain at 3 months. It doesn't mean that rate is 0. It means that rate is 1. So in other words, I can say that AN plus 1 equals to AN. So this is my difference equation. So if I want to put it into my formula, I can say AK is just equals to 1 to the power of K times A naught. Okay, but now let's consider this one. 300 is withdrawn from the account, meaning that the next step will be minus 300. Okay, so every time that you take that into account, and then you will be minus of 300. Okay, now not this one, sorry. I think this is minus 300 every time with this. Okay, so what happened about this one? I don't want to solve it. That's why I did purposely do it like this. Okay, now you can see that actually this one is, and it's okay. I'm going to build it like that. All right. I think we can take 10-minute breaks. Take 10, and then we trying to find the equilibrium.
Thank you, Doctor.
Welcome. Minus R. So you can just rearrange algebraically, and this is B over 1 minus R. Do you remember this form? Okay. And then R, obviously, R is not 1. So if it's 1, you can see that you have no equilibrium value. Okay. So maybe you can refer to your previous class or something like this. It looks something about what? Okay. So now let's try to recall our examples. So this is your equilibrium value. Okay, so if you recall the example number 4, which is the drug case. Remember this one? Yes, this one. Okay, you can see that B is 0.1 and then R is 0.5. So B equals to 0.1 and then R equals to 0.5. So you can see that A equals to 0.1 over 1 minus 0.5. So that is 1 over 0.5. It will be 0.2. Okay, so you can see that this is true because exactly what we did right here, this one, this our long-term value, equilibrium value is stable at 0.2. Okay, now let's check the next problem about this one, annuity. Okay, let's see. B is minus 1,000 and then R is 1.01. So example number 5 is about annuity. A equals to what was that? 1,000 minus 1,000 divided by 1 minus 1.01. So obviously that is 1,000 over 0.1. So that's just adding it, which is what we found before. This is unstable. And for example number 6, we can see that there is no equilibrium value because R is exactly 1, which is not what we want. So no equilibrium value when you have R is exactly as 1. Okay, now how about finding the solution? This is what we did just now. This is this. And we also did this. Okay, how about we want to find the solution just now before. Remember we have an plus 1 equals to R of an, and then the solution is A of k equals to R of k times A naught. All right. Now we want to find the solution when we have extra materials, constant material added into our difference equation. We suppose that we say that my solution will be the same thing as before, which is this part. But since I have additional material, I can say that the solution will be plus its equilibrium value. Why? Because as you can see that when k goes to infinity, this term will diminish and equilibrium value will remain. So I say the solution is like this, which is what we calculate before. So we want to test our conjecture by substituting our equation. Now what we do is we just substitute AK into the AN plus 1, so on. All right, now if we say like this by substitution, we say A of n plus 1 equals to R of AN plus B, and AN plus 1. So I want to make it this. So it will be R of n plus 1 times A naught plus B of 1 minus R. So I'm just taking this term, and then trying to compare with this. Okay, so this is just my solution because I have k and this is n plus 1, so this is also n plus 1. All right, any questions so far? No, right? Because I think that's, yeah, okay.
Okay, doctor.
That's straight to the point, right? So this is not an exclamation, this is multiplication. Right. Okay, and then RAN is just R times AN. AN is what? AN is just R of K times A naught plus B over 1 minus R plus B. So I'm just substituting my equation into my discrete dynamical system. Okay, now you can see that you can just, this is the same thing as, if you simplify this, you will get R of n plus 1 times A naught plus B over 1 minus R equals to R of, no, this is not K, this is, let me be, this is N because we are talking about N. This is N. So this is R of N because AN. Okay, so that is just A naught, just rearrange this, N plus 1. Okay, and then that one is just plus RB times 1 minus R plus B. Okay, now you can see that this one can be canceled out because positive on the different side. And then you solve for B, you can get that B equals to RB plus 1 minus R times B. Okay, now you can see that B equals to B. because this one is 0. You cancel by that one, and then so the result is identity. So you can say that solution to that equation is this expression for this discrete dynamical system as long as R is not equals to 1. Okay, so this is our solution. All right. Now, let's remember our nonlinear discrete dynamical system. If you remember that last time we did the yeast population, and the yeast population looks like something like this. You increase, and then at some point it will goes to a carrying capacity. Stop at that value. Okay, now we want to rewrite this into this formula because why? Because it looks simpler compared to this one. Okay, because you can see that this is like in terms of an plus 1 plus equals to R times 1 minus an times an. So that's easier to look compared to this one. Just rewrite that. And then R equals to 1.546. Now, what we want to do is we want to explore the long-term behavior related to the rate, or maybe we can say rate is constant. We can say to the constant parameter and initial condition. So we want to see how does it looks like when we change the rate and we change the A naught, our initial condition. What's going to happen to the solution and the sensitivity of this system. You can see that the nonlinear dynamical system is quite different than the linear dynamical system, because you can see later that this increase by a really huge amount. Let's recall just now when we have a linear, the linear meaning that the ratio is 1:L. But if it's nonlinear, in this case, quadratic, for example, now we have the ratio of 1:L squared. So small changes in rate or maybe small changes in initial condition may be a huge factor in terms of the long-term behavior. Okay, now let's see what's going to happen if we plot this as exactly as displayed. So we have the solution when, let's say, my initial condition of amount of population is 0.1. This is related to Pn. We can see that this is my equilibrium value. So about what? About 0.35. When I start at 0.1 and then my constant parameter is 1.5, about 1.5. Now I want to change while keeping a equals to 0. I want to keep this one, but I want to change my rate. Okay, now let's try to increase my rate. So if I increase to R equals to 2.75, you can see that this is oscillation. Oscillation, but it will goes to equilibrium value. We still start from 0.1. Okay, now let's try another value. 3.25, just increase by 2.5 at 2.5, yeah, 7.5. Okay, now you can see that this is like a periodic oscillation. Why periodic? Because you can see that this is the same, but same value, same on the upper limit. And the same thing also for lower limit. So you can, this is called double oscillation period. This is called double oscillation period. So this is called double oscillation period. Why double? Because you have one value and one value on the top and two on the top and on the bottom, the same thing going. This is going on infinite until infinity. Okay, now if I increase my value, you can see that on the top we have 1, 2, and we have 1 and 2 and 3 and 4 at the bottom. So this is 4 oscillatory period. You see that? And then if we increase more, you can see that the sensitivity to the rate, sensitivity to the rate is quite fast compared to the linear problem. If you recall that this one, let me show you. Let me show you this one. Where is my case? You see that it is more okay compared to that one. Okay, that this is because we have too much spaces right here, because that's why it looks like this. Okay, let me go back forward. All right, this one. Okay, so that because this one is just 50 times step, just now it was until 100, so that's why you can see it's more close together. Right now, do you want me to increase? Yes, try again. 3.555. Now you have several different values. I think this is 4 on the top. Let's say, let me see. Yeah, it's different. 1, 2, 3, 4. So that one is, yeah, this 4 is different than this one. 1, 2, 3, 4. And then you have the same move at the same period. for the other 4. So this is 8 oscillation. And if we increase more, you can see that you can no longer locate all the limits, because now this is called, let's see, this is called chaotic behavior. The limit on the upper limit and the lower limit is everything. I don't know, that's just my word. So this you can understand that it's scattered around, and then you cannot figure out the weight. It's no longer in periodic. Just now you can see that this is quite good, but this one, it's different. So this is a chaotic behavior. You can no longer say it's just oscillatory, chaotic. All right, any question? Any question before we move on to system of difference equation? All right, so I take it as no. And system of difference equation, usually this is talk about game theory. One example, and we can also talk about what was that? Elements, finite elements. This is also in system of difference equation, mass system, double or triple mass system, mass spring system. So you can have a lot of examples, but in most cases, we talk about this one, game theory, meaning that you can have one is competition. Number 2, you can have something like a company, not a company, something like something helping each other. What was that? Helping each other. Helping each other. Helping each other, just helping. Or like a symbiosis. I think symbiosis. And you can also have like prey and predator. And so on. Okay, let's look at what we want to do in this kind of problem. We want the same thing. We want to explore the long-term behavior of the system. Will it remain to the equilibrium value? Is it going to approach the equilibrium value? Is it going to be aberrant to the equilibrium value? And then we want to find the sensitivity of the solution. Number 1 is to initial condition, and number 2 to perturbation. What does it mean by perturbation? Okay, initial condition you understand because this is at t equals to 0. So my question is, for example, if let's say I'm going to give you an idea. Let's say my concentration, or maybe my population going to this way. And the other population, let's say I start from here, maybe going that way. Okay. And if I have my, is it going to be to approach my equilibrium value or not, and so on, it based on your system of difference equation. Okay, let's look at an example. Okay, hawk versus owl. So suppose that in a habitat you have two species. One is hawks and the other one is owls. And these two species are competing for survival. And this is your assumption that no other species present. Okay, and this one is just, you can read it, this is just talking about proportionality, and you can see that if I say ON O sub n, delta O sub n is proportion to a constant K1 times ON, and then the change in hawks at n, our n time is just K2 some constant times species of hawks. And then one species, this is important, one species is going to diminish the other species. So meaning that with the presence of other species, the original population will decrease. It depends on that. So I assume that this is my difference equation. And this is another difference equation for the other species. So K3 is just any constant and K4 is just any constant that we will check the sensitivity of that constant. Okay, so this one, for example, if Hn is increasing, then obviously this one is decreasing, and so on. Okay, now we want to solve for n plus 1. So solve for n plus 1. Remember that how do I get n plus 1? So this is just delta On equals to O of n plus 1 minus O of n. Okay, and then delta H of n equals to H of n plus 1. Did I resume my minus Hn equals to this. So equals to this. So this is how I get the expression for next timeline, and this is the expression for the next timeline for the hawks. All right, and then make sure that the constant are positive values. Okay, and then we just choose the values of K arbitrarily within reason, meaning that it's not too small and then it's not too huge, or not too huge or not too small. So I'm just choosing any value. Just put why I put like this. So for example, if I say 0.5, that doesn't make sense because it means that it will increase by rate of half. That's not make sense. Just that's why I highlight right here within reason. So for those who are already talking, who already have their own, let's say, concentration from previous study, that's also okay. Or maybe you have experimental values, that's also okay. So actually this is based on previous studies. All right, so now we plug in these values into H equation and then try to plot. All right. Oh, before that, I want to talk this. Okay. Now, before that, before we go to the plugin, to the graph. Okay. Now let's see. This one. All right. So if I plug in my value, I will get this value into my equation. All right. What do I get? I'm talking about the long-term behavior. Okay, so the long-term behavior meaning that ON plus 1 is just equals to ON. This is just equals to O. And the same thing for Hox, HN plus 1 equals to H of N equals to H. Okay, so I can substitute into my equation. So when I substitute it, it becomes O equals to 1 plus K1 times O minus K3 times O times H. And then for H, I have H equals to 1 plus K2 times H minus K4 OH. Okay, now let's look at the equilibrium. You can see that if I rearrange this, let's plug in my constant. I can see that plug in constant. Q1 to K4, I can see that O is just equals to 1 plus K1 is 1.2 times O minus K3 minus 0.001 OH. I think I better put something like this to differentiate between 0 and O. Okay, I want to put like that just to differentiate the letter and the numbering, right? Okay, now if I put it for H equals to 1 plus K2, that is 1.3 H minus K4 is 0.002 OH. All right. Now you can see that the value, there are two values for O when it will be 0. So we can see that one is this equation is 0, equation number 1, and equation number 2 when O is equals to 0 and when H equals to 0. And another one is when H equals to 200 and then when O equals to 150. Any question? How do I get this value?
Doctor, I don't understand how you got H equals to 200 and O 150.
All right. Now let's try to rearrange this. Okay, now because I skipped step. All right. Now let's make it this one. Where is my cursor? Okay, now one is we can choose. Let me rewrite that. Okay. Now we have one is O equals to 1.2, 1.2, 1.2. Let me 1.20, right? Minus 0.001 h, and then h equals to 1.3 h minus 0.002. Is it 0.01? Yeah, I think that's correct. OH. So if I rearrange this, and then I put 0, that just bring this to that side, and then bring h to that side. So that will be 0.2 of this minus 0.001 equals to 0. Okay, because I bring that one to the right hand side. And then that one is just 0.3 of h minus 0.002. H equals to 0. All right. Are we good so far?
Yes, doctor.
Yes.
Right. So you can see that this one is 0. This equation is 0 when owl is 0. Or maybe this one is equal. So I can see that 0.2. This is equals to 0.00. So excuse me, because we have too many 0, and also the letter O. It's, oh my God. I just erased everything. Sorry. All right. Sorry. So this is 0.2 of this equals to what just now? 0.001. Yes. Okay. Yes. So you can just cancel this one, and h is just 0.2 divided by. So that's how you get 200. Same thing for the other one. You have 0.3 h equals to 0.00. I think, is it 2 h? Yeah, and then you can cancel out h on either side, so we can see that the value of owl is 150. So we have two equilibrium value. One is we have 0 and 0. And then number 2, we have 150 and 200. So this is your equilibrium value, because it satisfies the condition, the equation on this one and also this one. Okay, now let's try to use this is trivial because it doesn't change anything. Okay, now let's use this as initial condition. I need to be aware of the time. Okay, 5 minutes, then we will talk about that after this. All right, now use this as initial condition. Okay, now if I start owl at 150 and hawk at 200 population, you can see that this is what we get, the same thing that we predicted. This is our long-term behavior or equilibrium value. Okay, so that's what we get from our algebraic manipulation. Now let's just change this. Let's change our initial value by a really small amount. Let's say, in this case, I start with, say, I think this one is 100, or not, initial condition as 151, and this one is less than 200, 199, I think. Yes. So you can see that if I start my population just increase by 1, and I will increase my population tremendously. However, if I start my population right here at the same time, then you can see that the hog population will decrease to 0. Now, if I change my initial condition just a little shy from the initial condition, from the equilibrium, which is 149, and then I add just 201, just one population extra from the equilibrium value, you can see the reverse results. One is increasing tremendously, and the other one is decaying tremendously. And let's say I start, this is close to just now equilibrium 150 and 151. Okay, 150 equilibrium value, nothing happened. 151 increasing, 140 decreasing to 0. And then if I talk about this one, my equilibrium value is 200, 199, and then this one will be decreasing and this one will be increasing. So it's quite sensitive to the initial condition. Let's say because this one is quite small, quite close to the equilibrium value. Let's say if I change this into something else. Let's say I start with owl population. No. My initial condition equals to, I think this is 20, and this one is also 20. So initially you can see that the value of owl is increasing, but eventually it will die out. But for the hawk, you can see that it will increase tremendously. So that's the behavior after long term when you put system of difference equation. Okay, now what's the lesson of this one is that if that equilibrium value is sensitive to initial condition as t goes to infinity, meaning that there is no when you change the initial condition, the equilibrium value change accordingly. So you can say that that value is unstable. That equilibrium value is unstable. All right. I think I can stop at this now because yes. Any question?
Yeah, can I quickly ask? So from the computation, does it mean we have two equilibrium, which is 0, 0 and 150 and 200? Or
yes, yes.
Oh, so both are the equilibrium.
Yes, both are the equilibrium, but the 0, 0, 1 is trivial equilibrium because the 0, 0, because if you start from 0 population, after time as t goes to infinity, Okay, after t goes, it will stay at 0, 0. So that is trivial equilibrium value. It doesn't
Okay.
make any sense into our model because we didn't start at anything. So obviously we end up with nothing.
Okay.
But this
Thank you, Doctor.
yeah, sure. But the thing that we want to investigate is this value. So we will talk about this one. So this is unstable one. All right. I think that's, yeah, we are at the end of our session. All right. Any other question? All right. So since we have no question, then I will leave it this time. And then please go to, let me, excuse me, change my setting. So if you go to this link, okay, make sure that you are able to open it.